Of course, yes. Why wouldn't you? Mm-hmm.
You had to analyze like the sonnets.
Let's say we want to find the surface area for, hello, z equals x squared plus y squared. Well, that's a strange orientation for that table. Find surface area for this surface under z equals 9. Okay, so that's what we're given. And just so that we see what we're working with here, you should know what the graph of that looks like. That's your standard paraboloid. Z equals 9 is just the plane that cuts it off. So I mean, we can just call this up here z equals 9. So then the surface area that we're trying to find would be this part. Okay, so we're trying to find the surface area of this bowl, or whatever you want to call it.
On the inside.
Just on the outside. Well, that's the definition of it, yeah.
Oh.
Yeah. Okay, so to find the surface area, we do the double integral over the region R. And yesterday we derived the formula. What was the first part? So if I look at z, what would partial x be?
2x
So 2x squared plus
2y
2y
squared
squared
plus 1.
plus 1 dA. So that's the setup. Now we just have to figure out our bounds. I will clean up the square root a little bit. So that's 4x squared plus 4y squared plus 1. And now keep in mind, when we set up our bounds for R, we're looking at the projection of the surface onto the xy plane. And if you see it, it's just what? It's just a circle. What would the radius for the circle be? 3. So for a couple reasons. One, since the region is a nice polar region, and we could easily switch over to polar, that's what I would do for this integral, is switch it to polar coordinates. So instead of the square root of 4x squared plus 4y squared, that would be the same as 4r squared, good. And then we need r dr d theta. And then our bounds for the radius would be from 0 to 3, and then theta would be from 0 to 2 pi.
So it's not symmetric.
Well, it is.
So could we?
You could.
From 0
Yeah.
to pi/2?
Sure.
pi/4?
Yeah, that should work. Or pi, multiply by whatever you wanted. Yeah, lots of options. Okay. In the interest of time, is it worth going through this integral? Can you see what to do here since you have the r on the outside? You could do a u substitution where u is 4r squared plus 1, and then you have almost u outside, or du out here, and then you can go from there. Yeah. So I mean, if you want to try this later, here's what the answer should be: pi over 6 times 37 to the 3/2 minus 1, or equivalent. Yes?
Is R like part of the integration process, or is just a random letter?
It's not random. That's part of the integration process. Yeah. Yes?
Wait, so just double checking, you know that R equals 3 because you plugged in 3 for Z and then, like...
Well, there's a couple ways to
or
do it.
9 for Z.
Yes, you can plug 9 in for z, and then you get the circle x squared plus y squared equals 9. That would be the other way. Yep. Yes.
Are the values they are generally 0 to 1?
If you're going all the way around, yeah. Other questions? Okay, so again, we're going to focus on the setup. I will do the next one in detail since it might be worth doing one with the trig substitution. So let's go through that one. Let's say I want to find the surface area of z equals the square root of 4 minus x squared above the region R, where it's 0 to 1 by 0 to 4. Okay, so again, picture helps. This is just a cylindrical surface, right? Because there's only two variables. So how would I sketch a graph for this? What plane would I start on? The xz plane? Okay.
So it would come out toward us, and then that's just the plane goes to the right.
Come out towards us. And then goes right and left, right? So something like this. And you have the other portion back here if you want. Okay. So then the rectangular region R is from 0 to 1 and then 0 to 4. So here's R, and if I map this up, then it's going to correspond to maybe this portion. So this is the area that we're trying to find. All right, so let's set this up. The integral would be the square root of partial x squared. So here that would make that over the root of 4 minus x squared. And then we would need a negative 2x times 1/2, so that's just negative x squared. There is no y, so that's plus 0 and then plus 1. And we'll go dy dx. And since y is what I put first, it'll go 0, 4, 0 to 1. Okay, so let's just clean up the integral. That's the same as x squared over square root of, oh, no, no more square root, sorry. And just to make things simpler, I'll make 1 the same as 4 minus x squared over 4 minus x squared. Which is kind of nice. The x squareds in the numerator cancel. The square root of 4 is 2. And then we're left with the square root of 4 minus x squared in the denominator. Now it would be fantastic if in the numerator I had what? An x of some sort, right? 2x, x, whatever. We don't have that x that we need to use u substitution. Okay, so this is where we'd have to utilize a trig substitution. Okay, and the idea, and again, this is in the handout that I have on Edmodo if you're interested or if you've forgotten how to do this. The idea is to do a trig substitution for x that would turn this into a square trig function. Okay, so,
But are we doing it with y first?
well, oh yeah, I'm getting ahead of myself. Plug in the bounds for y first, sorry. You'd get 2y, plug in 4, So after you integrate with respect to y, you get 8 over root of 4 minus x squared dx. Sorry about that. I'm getting excited for trig here. Okay. Now we're going to use a trig substitution. And in order for this square root to entirely go away, we need x squared to produce a 4 and sine maybe. So if I do 2 sine theta, then that would actually help because when I plug in the 2 sine theta, we get 4 sine squared. Pull out the 4. What's 1 minus sine squared? Cosine squared, you take the square root. Everybody's happy. There's no more radical, right?
How can it just
How
X?
is it?
How can you just say X?
How, yeah, how can you just like assign
Because
x
it's
an
a
arbitrary
circle,
value?
and that's like kind
It just makes it easier.
Yep.
of wait.
You'll
how
see.
do you
What
know
would
what
dx be?
Two, yeah, two.
2 cosine theta d theta.
X is R sine.
No, I see how it makes it easier, I just don't see how you can do it.
Well, what else could you do to integrate?
I don't know.
Exactly.
No, I'm saying like, what
Don't
did,
integrate.
what did you just do? How did you just say X is 2
Yeah.
sine?
Yeah.
Look at the denominator. Again, if you did not do this last year, look at the handout. I have everything step by step on there. It's on the folder in Edmodo. The point is you want the square root to not be down there, right? You can't just get rid of a radical unless you have just a single term down here. So if you can do a substitution for x that would make this become just one single term that's squared, then we're on to something. And if you and it actually doesn't have to be sine, that's the convention. What else could you do if you wanted to? You could use cosine, right? Because cosine would be the same idea, except dx now would be negative 2 sine theta d theta.
Like, is there a point where you have to resubstitute back?
It depends on if you switch the bounds or not. So I'm going to work this through and actually leave it in terms of theta. Okay? So here's what the new integral is going to look like. Okay?
Wait, how did you get from, like, how did you take out the first integral? What was
The integral of all of that would be all of that times y. Plug in the bounds, which is 4 and 0, and then it just becomes an 8.
2 sine theta or c sine theta?
That's a 2. Okay, so if I rewrite the new integral, I'll worry about the bounds in a minute here. We have 8 over square root of 4 minus 4 sine squared theta, and then dx is 2 cosine theta d theta.
That's good. Then you take out the 4.
Yep. So that's 8 over 2, 1 minus sine squared theta for the square root. 1 minus sine squared is the same as cosine squared. Whoops, no bounds yet. So then this would be 8 divided by 2, which is 4, over just cosine theta times 2 cosine theta d theta. We've reduced our integral from this ridiculous radical to just 8 d theta. So now the question is, what bound should we use here? How did I do what? Okay.
So they,
Some previous. As soon as I was up to away from.
8 divided by 2 is 4.
Oh.
Square root of cosine squared is cosine. We still have the original dx portion out here, and that's how we get 8 d theta. So now,
For this, you wouldn't be able to just go from 0 to either power 2 because it's not circular.
right, so here's what we can do.
Theta 1 would
All right.
be reverse sine.
What bounds should we use here? We know x was originally between 0 and 1, but what was x for here, our substitution? 2 sine theta, right? So you can use this inequality to figure out the bounds. In other words, 0 would have to be less than or equal to sine theta, which is less than or equal to a half. What angle for theta produces the lower bound, which is 0? 0. And what angle for theta produces the 1/2? There we go. So then this becomes 8 theta, evaluated from 0 to pi over 6, which is just going to be 8 pi over 6, or 4 pi over 3. Okay, I take it from you wanting to throw tomatoes at me that you haven't done this very often. How many of you are not very familiar with trig substitutions?
Or at least not
Well,
being
we
used
did like check identity.
No, we didn't do that.
Okay.
Or-
I have been told by the AP people that this is not part of the curriculum as much as it used to be because it's not really on the AP test. So if it's not on the AP test, or it wasn't taught to you last year, look on the handout. There's 3 trig substitutions that will be helpful in the scenarios where you have radicals of squares. A square plus a square minus a square, okay? And where you have no use substitution that you can utilize. Will?
So, this trig substitution is different from like converting rectangular coordinates to polar coordinates?
A little bit, yes.
Okay, so like that, like you changing the denominator to like 4 minus 4 sine squared theta is different than changing like
Yes,
x
we're not
to-
switching it to polar.
Okay.
Right. A little bit different.
It's like a use substitution, but
Yes.
you use more.
Yes, it's exactly a use substitute. I mean, look, you can substitute whatever the heck you want as long as there's a link between the 2 variables. The thing is that we substituted a trig expression here because
It works.
here's the key. We want to get a binomial expression to turn into a square expression, right? Because we can square root that square expression, and then good things happen after that once the radical's out of the picture. Okay? So that's the whole point of this. Yes?
So, it didn't have to be 2 sine theta.
It could have been 2 cosine theta.
But I mean, you could substitute other things for x. That was kind of just for this
Put
problem.
anything in there? You could do
Anything that helps you
tangents?
solve the problem.
Anything that helps you solve the problem, as long as you link the bounds back to the new variable
Okay.
from the old variable. Yes.
You could put anything.
We like
Use
Yeah.
substitution.
But I mean, there's really not many options there. You can try to be creative and do other things, but these are the two, well, there's a reason why sine is a convention. Why would sine be better to use for x here than cosine? The derivative doesn't have,
The negative.
yeah, we don't have that negative in there. That's why we use sine. You could use cosine if you wanted to.
Use tangent.
I don't think you would have an identity to use if you use tangent. If it was plus, because isn't 1 plus tangent squared secant squared? So if this was 4 plus x squared, I would definitely use like 2 tangent to get the secant squared in there. So you guys are starting to kind of see it now. Okay, the point is you want to play with it so that you get a nice trig identity that you can substitute for it. Yes?
Is it 2, do we plug in 2 sine theta so that way the 2's row is not the radical?
Yes. Because you want to produce the same coefficient. So if this is a 4 minus, let's say it was 9 minus x squared, you'd want to use 3. Because you'd want to be able to factor out the common factor so you get exactly the identity that you need to use for cosine or sine or whatever.
So will we be seeing many points where like the initial problem is over square root 8 minus 3x squared?
No. I don't think you'll see many of those now. Usually it'll be more like this, or there will be a clear, like the first term will already have just the fraction that you need, and the x will be with a coefficient of 1. Other questions? Okay. Let's move on. So anyway, we did one example of finding surface area, setting it up. This was the answer. Again, not hard. Just remember how to utilize the formula we derived yesterday in class. We did another example of finding surface area where we had to do, I guess, something you're not very used to doing. So I do recommend going through that handout and kind of following those examples I laid out for you. The last half of the section focuses on parametric representation of surfaces. Okay, so we've already done parametric equations before, but back in chapter, what was that, 12? I think it was 12. We did x equals x of t, y equals y of t, and z equals z of t, which produced what?
Curve.
Yes. Or a line, but more generally, a curve. Okay.
It's like you connected all of the endpoints of the vector.
Now, if we do two variables for x, so like x of uv, y equals y of, uv, and z equals z of uv, instead of producing a curve, now this will produce a surface. Okay, and now here's essentially why. So think of u and v as kind of like x and y. And as you vary the coordinates u and v, so for example, if you hold u constant, so let's pretend u is constant for a second. So let's hold u constant. Now I'm allowed to pick any values for v that would satisfy the equation, right? So we're going to get a collection of points on this line. Does that make sense? But if I vary u and slide it around, essentially now we get what looks kind of like a plane. Okay? So we're not going to have just a curve because this is only a little portion of all the points that would satisfy the parametric equations, particularly where u is equal to c. But we can make u anything that's allowable. So we could have u, let's call this c1, we could have u be equal to c2. And then we can find more values of v that satisfy all that. And, I mean, obviously we're missing all the in-betweens, but eventually you just get a collection of points which represent a plane, on the UV plane anyway. And then that UV plane will correspond to some surface above it. Okay? So, in 3 dimensions, here's what it looks like. It doesn't look anything different from what we've seen. We have some surface, and if we do all the u curves, u curve, u curve, u curve, u curve, and if I do the same but do all the v curves, you get a surface. Okay? Now, our definitions from before, when we did vector-valued functions, I'm glad someone remembered that we tied parametric equations to being components of a vector-valued function. So, similar to this, we can do the same with our new parameterization, which will be in terms of not t anymore, but u and v. And I'm off the screen. Sorry. So then this would be x of uv, y of uv, and z of uv. So now this vector-valued function would point not only to a collection of points which form a curve, but a collection of points. So if we go back and tie this to the origin, all these vectors would span the entire surface. It's kind of hard to draw because there's an infinite amount of them and it's difficult, but that's essentially how it works. I can be honest with you and say that we're doing this because in some instances, having things parametrically represented might make things a little easier to comprehend later on. It's not the most convenient necessarily per se as far as calculations are concerned, so we'll go through the ties between the two variables. There is one nice application though which will tie back to Calc 1. Something about solids of revolution.
Yay.
Okay.
No, that was terrible.
Okay. So anyway, let's go through a couple examples. Let's say z equals the square root of 9 minus x squared minus y squared, and we just ask for finding a parametric representation. So we want to find x, y, and z. Now, in a scenario like this, it's kind of easy to see that there's already two variables for z, right? So perhaps we should let x equal what? And y equal v. So that z would then be the square root of 9 minus u squared minus v squared. Okay, this is just one representation. If you wanted to, you could do cylindrical, x of r theta, y of r theta. So now our u and v are two different variables. What would x be if we go to polar here? And y is? And then so z would have to be now the square root of x squared minus y, or a negative x squared negative y squared is just the same as, yep. So this would be another representation parametrically with a different set of two variables producing the same surface. Okay, so there's different ways to represent it. I'm just showing a few of the options, but in general, as long as you have z equals f of x, y, you can pretty much stick to something like this. Where you can let x be u, y be v, and then z would just be whatever you get when you plug in u and v for x and y.
If we wanted to, could we just make x equal 2u or 2u squared plus v?
Yeah, lots of. The only thing that's going to change if you mess around with what variation of u and v, like 2u or whatever you plug in, is that the surface will be traced different at a different rate, but the surface will still be there. It just might take more values to produce the same region, if that makes sense. Okay. Okay. So here, let's try this example, and then from this example, we will try to get to the solids of revolution. Sometimes, like in previous units, they'll actually tell you what variables to use. Okay, so here's a scenario of that. Find parametric equations for the portion of the right circular cylinder x squared plus z squared equals 9 with y between 0 and 5 in terms of u and v as shown. So you're going to see a picture here. They restricted y, and if you think about x squared plus z squared equals 9, that is a circle on the xz plane, right, with a radius of 3 extruded along the y-axis, so something like this. And yeah, it says we're strictly between 0 and 5, so we can say that this is where y equals 5 right here. And now, here are the variables. This is u. And there's v. V is the angle. So u looks like is simply the what? The y coordinate. Okay, and then to find v, we'd have to drop perpendicular down to the xy plane, and then connect whatever y coordinate we have to the y-axis. We get a little right triangle there, and then we're using v as that angle.
So it's sideways going.
Kind of, yeah. So you'll see why we're going through this example, because we're essentially deriving something without doing the derivation. But so let's just kind of write down. We already have one observation, right? We said y is the same as u. So now we just have to find x and z. Well, over here, the x-coordinate, wouldn't that be the same as this side of the triangle, that length? So what would this length be? What is it? 3 cosine v, good. Because the radius, the hypotenuse, we didn't draw it in, but if the radius of the cylinder is 3, the hypotenuse for that triangle would be 3. So-
you was coming out of, I'm sorry, how do we know it's 3?
The cylinder has a radius of 3.
And that's going to the center?
That's going to the surface of the cylinder, not the center of the cylinder.
Oh, yeah.
Well, it's coming from the center. The center of the cylinder is the z-axis. Does that make sense?
Yeah.
Okay.
When you post in V, like, that part isn't touching the cylinder, is it?
No, it's not quite all, well, it's not quite getting all the way out to that part, no. And then z would be basically the height of this triangle, right? 3 sine v. Okay. And now let's write down the restrictions. Since y was between 0 and 5, we would say that u is between 0 and 5. And then what are some natural restrictions here for v?
Has to be less than 90 degrees.
If it's less than 90, then we're only going to get a portion of the cylinder. 0 to 2 pi, yes, has to be, because we want to get all the way around, right?
Wait. Yeah, but like,
If v is only between 0 and let's say 90 degrees, right?
then how can you drop it, drop it perpendicularly?
Well, this triangle can get flipped over, right? And we can do the same thing but underneath. I mean, it's kind of hard to draw. But imagine triangle on the xy plane, flip it over. We got to get the bottom part of the cylinder, right? What kind of angles would we have to have there?
Looks like you're starting from here, you gotta go all the way.
Yeah, so if we're starting here, right, and we say that v is between 0 and 90, that's only here. How much of the cylinder is that? That's just a quarter of it.
Yeah, I know
Right.
you have to go around. But
So that's why it's between 0 and 2
how can
pi.
I create a right triangle if we goes up?
Well, it's like a collection of right triangles.
You're using.
He's just.
Right. This is just one of the right triangles that we're using to get what the variables actually are. Does that make sense? So this triangle will vary depending on what u is and what v is. Because this, you guys see what we're talking about here? Like this point, is it on the cylinder or not? This one.
Yes.
That's
And if you vary u and if you vary v, then you're going to get what?
the whole.
The whole surface. Does that make sense? Okay. Now, let's go on to something more general. This last example kind of hints at solids of revolution a little bit, because this cylinder could be thought of as a curve that's been revolved around, let's say, what axis would that have been? Y-axis. So y-axis is the axis of revolution. And now notice that was the one weird oddball case in here, right? So the general equation. So let's say we want to, if we want to revolve any function, say f of x, around any axis, let's just start with x. Then we can say x is going to be u. So whatever the axis of revolution is going to be, that'll be our u equation. And now y and z will be f of u cosine v and f of u sine v. Okay, so for example, and I'll actually pull out some pictures here in a sec. If we have y equals 1 over x, so these are not very difficult problems. And I asked you to come up with the surface equations if we revolve this curve around the x-axis. Which, by the way, let's see, what would that look like? 1 over x looks roughly something like that, right? So if we revolve this around the x-axis, we get something that looks kind of like that.
It's like a funnel.
I can't really draw it too well, but my computer will draw it for me here in just a minute. Anyway, so now we get a surface when we revolve this y equals 1 over x curve around the x-axis. And the equation for that surface, we can very easily write parametrically. What would the parametric equations be?
Maybe
X
X is
is u.
1 over
Yep. And z is 1 over u sine v. So this would be the parametric representation. If I can quickly switch modes here.
If y and z were switched to
Actually, that's a great question. You can switch the cosine and the sine. Is that what you're asking? The only thing that's going to do is just switch the direction, but it still produces the same surface. So it would be okay either way. There we go. So let's go to So I'm recording, but also connected to the Apple TV. I don't know how this is going to work, but let's hope that it does. Okay. So 3D graph. New equation from template. Cartesian surface, okay. And here's where we get to define things parametrically. So u, and this would be 1 over u times sine. They don't want me to use v here. They want t. So we'll do t. But it's the same idea. Oh, shoot.
That is pretty cool.
That is much better than I can do.
One of those thingies that the instruments that they play
Yeah.
then, like the horn thingy.
Yep.
It goes infinite.
Yep, it sure does. And you can do this with any curve f of x and produce lots of cool shapes. But anyway, and it's a lot easier to write these equations for the solids of revolution, for the surfaces anyway, parametrically, if you know what curve it is that you're revolving. Yeah.
Are we gonna have to draw this?
No.
Why doesn't it go in the other direction?
So what do
Can
you
they go
know?
in
Why?
It can. We're only defining. You see right here, it says t is from 0 to 10. So is you. So we're. That's why it's only doing that portion. We could mess with it and let's see.
What if you made
Negative.
YU and then X the side? Would
That is.
Anyway, we're not quite done yet. So we're gonna stop here. Tomorrow we'll finish 14.4. Whatever time we have left at the end of class, I'll just let you guys ask questions about anything you want to go over. Friday will be a discussion day as well. Okay, so then Monday we'll start 14.5, which is triple integrals, yes.